Okay, so let's talk about Unicode extended grapheme clusters. Uh, this is another part of UAX 29, and they're important. Well, they're important for two reasons. One is because they're important if you're rendering any text. Whoops, wrong thing. If you're rendering text, they're important, and they're also important um, if you are, well, if you're editing text, they're also important, which we'll talk about why in a second. And then lastly, they're important if you're using Swift. And that's because the Swift's character type, yeah, a second. Um, Here we are. Let's see. Apple. Swift's character type is an extended grapheme cluster. It should say this somewhere, a single extended grapheme cluster. Okay, so for Watt, this text editor that I've been making, and I should have said this is part of a series on this text editor I've made called Watt, and it's part of a playlist. And this is the third video, but if you want to start from the beginning, you should go to the playlist and start from the beginning. I've been making this text editor. As part of it, I made a custom text storage. So the question is how, basically how is the text of the document stored in memory? Um, and you could use a string, but if you have then lots of text, editing a string can become very slow. For instance, if you want to delete a character in the middle of a huge piece of text, uh, you have to delete that character and then copy everything over in memory. So I'm using a rope, which is text made out of a tree, except my rope looks a little more like a bee tree. Um, this is, I'll cover this more later, and this is all derived work from mostly Rafe Levine's work on Xi editor. B-tree is just it's like a binary search tree. It's an n-ary search tree with that is always fully balanced by construction and has a high branching factor. So here's an example. Instead of binary, this can have up to 5 branches. Yeah, so they call it order 5 here. And the leaves are, every leaf is the same height. I'll go into this more later. The important thing is I store text in a tree. The text is, and that's so I can get big O log of n operations for indexing and editing into the tree. And I wanted to reproduce the Swift string API, which is to say the text thing, the rope, is a collection of characters, and characters are extended grapheme clusters. Um, this is a somewhat, I guess, a unusual decision in programming languages. Most programming languages say that strings are, at this point, well, it depends on the language and when it was made. I think most modern-ish languages say strings are arrays of Unicode code points. Um, though you can get all sorts of representations like, uh, a string is an array of UTF-8 bytes, or a collection of UTF-8 bytes, but you can iterate over the code points. Or if you go back to languages that were first conceived in like the late 90s, like Java or JavaScript, um, the strings are sequences not of code points, but of UTF-16 code units, um, which are, for the most part, the same as code points, except for code points that are very high. Uh, and in that case, the UTF-16 representing a very high code unit in UTF-16, or code point in UTF-16, takes 2 code units, which are actually also code points. And they're the leading surrogate and the trailing surrogate. It's very confusing. The point is, most programming languages have something that is good enough until it's not. Um, and Swift seems to have this, I don't know, this idea that everything should be really good. And so Unicode code points characters are extended grapheme clusters, which we'll talk about in a second. And on the one hand, I understand why they did this, and I think on the other hand, every time Swift does something where it says this should be correct, it gets complicated. And here it gets complicated. So let's talk about extended grapheme clusters. UAX, the 29, the Unicode text segmentation um, annex, has a whole section on grapheme cluster boundaries, and it's long. Uh, I guess it's not, maybe it's not as long as the word boundary section that we briefly looked at last time, but there's a lot of stuff here. And in fact, there's both legacy grapheme clusters and extended grapheme clusters. So there's extended, here's legacy. The important thing, I think, is this first sentence. That what the user thinks of as a character, a basic unit of a writing system for a language, may not just be a single Unicode code point. That's the thing. And so an extended grapheme cluster is what the user might think of as a character. It's what renders as a character in the text editor. And I'm going to pause this video and come back in a minute because I just got a text. Okay, so where were we? I believe what I was about to say was uh, an extended grapheme cluster is basically hand wavy what renders as a character, what you would, what you would expect to see as a character, right? So H, that's an extended grapheme cluster. Now that happens to be made up of one code point. I know this. Um, some other extended grapheme clusters are made up of multiple code points, but it's something that you would sort of identify, that a reasonable person would identify as a single character. It's pretty close, though possibly not exactly the same to as a thing that that is uh, that is atomic for your cursor in a sense. Like if I'm here and I press right, the thing that the cursor goes to the other side of, that's the extended graphing cluster. I think that's not always the case because I think it's possible like that ligature is like a two F's one like two F's in a row where you have a typeface where like the first F is connected to the second F that you actually that I think might be an extended grapheme cluster, but you should be able to put your cursor in the middle of that if you want to delete the first F, or maybe you have the FI ligature where the top of the F goes into the dot of the I, and you do want to be able to put your cursor in the middle of those, but I actually don't know about that. But hand wavy, it's a thing that looks like a single glyph on the screen and that you would expect, if you're on the left side of it, you press right, the cursor jumps to the other side. So I put together this little app, and the code for this is in a gist, and I'll put it. I'll link the gist in the video description so that we can look at extended grapheme clusters. So as an example, here's the letter E, and it's a single Unicode code point. The number is 65. Well, actually, this is hex, so the number is not 65. Don't worry about that. The name is Latin small letter E, and this is a string. So if I type a bunch of things, we'll see all the code points. And if I type something more complicated, what looks like a single character to us, you might see multiple code points. So here's actually an example. This is going to be still a single code point. So if we type an E with an accent, this is one accent, or this is one code point. Latin small letter E with acute. The acute means acute accent. But there are actually two ways to represent this glyph, and I'll show you. I've done a little special stuff in here to allow us to type Unicode escape sequences and have them be replaced with the actual byte or code point, really, I guess. So I think if we do, I never remember, is it 42? Oh, there you go, 42. Hex 42 is B, right? So I type this, and as soon as I close it, it gets replaced with A. All right, cool. So remember, this is one way to type E, a single code point, or E with an acute accent. Another way to type an E is an E followed by the code point 0301, which gives you this still a single glyph, a single extended grapheme cluster with two code points, the small letter E, which is what you get just when you type an E right here, and then the combining acute accent. Combining means it combines with whatever came before. Um, and there are all sorts of other ways that you can end up with combining characters, or multiple code points in a single um, in a single grapheme cluster, extended grapheme cluster. So here, the cross fingers with the, or actually, let's look at, is this how you do it? I don't remember how to do skin tone selection. Well, whatever. Let's start with this. This is a thumbs up. It doesn't have a skin tone. So it's a single code point, thumbs up sign. And here's the a light skin tone, fingers crossed. And okay, the first one is this hand with index and middle finger crossed code point. And the second one is this emoji modifier Fitzpatrick type 1, 2. So the Fitzpatrick modifiers are skin tone modifiers. And the important thing here is that just like the combining acute accent comes directly the um, after the E in the previous example, that was, oh, well, that was this actually. Whoops, U0301. So there was the E and then the combining acute accent. Here, the Fitzpatrick skin type modifier combines with um, uh, the middle finger emoji. And you can have degenerate cases, right? So this is 1F, 3FB, right? So if I add one of those, 1F, 3FB, this is now just the skin tone modifier thingy, and it cannot combine with it can't combine with this E, and so it just gets rendered on its own. And similarly, if you just have a combining accent, it renders just as an accent, and also it kind of has zero width, which is weird. Or I guess it doesn't have zero width, but it is pretty small width. Um, so those are some ways code points combine. There are even more ways. So for instance, in this man and woman holding hands, let's see what happens when we insert this. Now this is just a single code point, man and woman holding hands. But you can also do things like, oh gosh, how do you, there's a way where you can, well, it doesn't matter. There's a way where you can like select the skin tones of each of them. But here, this looks like, well, this is a man and a man holding hands, but I think there's probably man and man holding hands. No, there is not. Well, whatever. Um, there we go. Okay, so let's do a man and woman holding hands, but with uh, skin tones, specific skin tones, like so. And then we can insert that. And now instead of a single code point, man and woman holding hands, this is like made of many code points. So it's a woman followed by a skin tone, followed by a zero width joiner, which is just a character that it's like kind of like a white space character, but it doesn't have any width. And you basically use it between two emojis to combine it into a more complicated emoji. I'm sure it has other uses too. Then there's the handshake emoji. Then there's another zero width joiner. And then there's the man and the emoji modifier, the skin tone modifier. And so it's like, okay, this is a woman with a skin tone. It's joined with a handshake, and then it's joined with a man with a skin tone, and that all ends up as one extended grapheme cluster. Um, the things to notice are sometimes um, you don't need a special joining character or code point, and sometimes you do, right? And if you remember going back to this, right? Oh, whoops! No, I got too tall. Let's just do it here. If we go back to this, for the combining characters, we don't need a joiner, right? But perhaps parents, is this parents and child? Yeah, right. So here's an example. This is a weird representation, I think, because it doesn't have any skin colors or maybe genders, but adult, child, that's a family, right? Um, and I wonder if we were to like press and hold on this, if no, there's definitely a way to like have have a family and have it look like people. Um, but I don't know it, and so we're not gonna. Or like, here's an adult and a child. I mean, what if we have? Oh, you know what? I bet we can build one, right? So if we get something that has a zero with joiner, so I remember what a zero with joiner is. Okay, 200D. So if we do a man, um, just a plain old man emoji. I don't even know. Is this a man? Let's see if that's just like a normal everyday. No, that's a standing person with a male sign. Oh my gosh. Okay, let's try again. The man is 1F468. Okay, so 1F468. We have a man, and then we can add a zero width joiner, uh, 200D, and it doesn't show up as anything, but let's add another man, 1F468. Oh, maybe we have to add a handshake. Anyway, the point is, this is complicated. There are lots of rules. I don't know them. I definitely didn't program them. We'll talk about what I had to do in a few minutes. There's one more category that's, oh, did you see that? When I pressed delete, I pressed it once and it deleted everything. Because even though it's rendering this even though it's rendering this, it looks sort of separate. It's treating it not as an extended grapheme cluster necessarily, because I don't know that it is, but it's treating it, the cursor can't subdivide it, and it's a single thing that can be deleted. So this is all very interesting. The last thing is to talk about flags. I think the way flags are done is very funny. It also has like a really annoying aspect to it. Um, so here we have two flags and we have four code points, and you'll see that the each flag is represented by two, like they're basically these 26 code points that are isomorphic for the letters A through Z. But they're not just the letters A through Z. They're these regional indicators, and you combine them with the country code, and you get the flag. And so it's two letters per flag, and it's a clever idea. It has and so it has a flaw. The flaw is that uh, well, in order to know, like, how do you know? Let's just add another U1F1FA, right? So now, okay, they come in pairs, and so because this one isn't paired with anything, it kind of lives on its own. And so this is degenerate. It's not something you normally see, and of course we can fix it by 1F1F8, and now it's another US flag. Um, the important thing here is the way you know whether, like the question is, okay, so you have this long string of Unicode of regional indicators. How do you find out where the grapheme cluster boundaries are? And the only answer is they're at the even boundaries, which means to know whether say between the G and the B, if the boundary is between 2 and 3 or between 1 and 2, you have to start at the beginning and work your way down. And what this means is if somebody gives you, 1 billion a file with 1 billion regional indicators, uh, you may fall over trying, in order to find out where the grapheme cluster boundaries are, you have to start all the way at the beginning. And, I can imagine basically denial of service attacks that come from just having millions and millions of regional indicators. And I don't know how most systems deal with that, but that's the last bit of it. Okay, why are we talking about extended grapheme clusters? Well, if we go back to, you know what? Actually, there's a new blog post that Thorsten Ball wrote about sum trees, which is a sum tree is basically the name that Z gives to this same data structure. So the sort of same data structure that's used in Xi, which is a rope that's made out of a B tree or something resembling a B tree. So this is a normal rope. It's not necessarily balanced. Here is a rope that this is what Z calls a sum tree. So the nice thing about this is you get this sort of big O log n. You have logarithmic operations, both accessing and modifying these trees. And in order to do that, you have to make sure that your leaves are bounded in size. What you bound it at is up to you. I have arbitrarily chosen in mine 1,000, like the maximum size of a leaf is 1,023 bytes, really, and I'm assuming Unicode UTF-8 encoding. So really, it's 1023 UTF-8 code units. Um, and I've decided that you can't have a code point split a leaf boundary. So if you can't have one byte of a code point on the left on at the end of the left leaf and another byte of the code point at the beginning of the right leaf, and that simplifies things. Um, the problem with extended grapheme clusters and characters in Swift is that you it's just this is it's just it's crazy making. Um, you you need, in order to have these logarithmic operation, like logarithmic uh, what's the word, properties, in order for this data structure to retain logarithmic properties, you need to make sure that the leaves are all bounded in size. Because you can imagine, if you put the entire string in one leaf, well, then you just have a string, and you have all these linear properties. So um, the the reason this is a problem is because extended grapheme clusters can actually be unlimited in size. Um, so we'll do here as an example, right? If we do 0301, so we have a combining acute accent, and then we also do, I don't know, I'm going to guess 0300 maybe, which is a combining grave accent. You can see that now that that has both accents, and you can sort of stack these to your heart's content. So first of all, I can just add another combining acute accent, and actually the acute accent got a little darker, I think. Um, and then we can also, I don't know, 0302. So now it also has a circumflex, right? And this will just kind of work, but what it means is that a character has no bounds. Like there's no maximum length to a character, to an extended grapheme cluster. Um, and sometimes you see on Twitter, like people have, there's a name for this, and I don't remember what it is, but like it's like letters with a million accents that sort of like stack all the way out of the line, and take up 5 lines of text or something, and it looks very glitchy, and people enjoy that. Um, and what that means is you can't make the same simplifying assumption for extended grapheme clusters that I made for characters, or that I made for code points, which is to say, I'm allowed to say, without worrying too much, that you can't have a code point split leaf boundaries. And that is, what that means, because each code point encoded in UTF-8 is between 1 and 4, I think, bytes long. And so it means I'll have some slot, maybe some leaves will have 1021 bytes instead of 1023, but nothing, it's not unbounded, right? And so you never get into the situation uh, where um, you never get into the situation where one leaf grows to be the entire string. But if you were to say that we won't allow characters to split leaves, like that a character must be entirely on one leaf. Uh, you could have a leaf or like a string that has a single character that is like 1 gigabyte long, and it just you no longer have any of the log n access properties. It's just a normal string, and everything is big O of any iterating across characters is big O of n. Of course, iterating across bytes is order one. But because characters are variable length, and also code, the encoded code points are variable length, that you end up in a bad situation if you allow these leaves to grow infinitely, or to any length. And so what this means practically is I have to allow characters to span leaf boundaries. And in fact, because characters can be arbitrarily long, uh, I have to allow characters to span an arbitrary number of leaf boundaries, so that like this entire tree might contain only one character. And remember, in Swift, a character is an extended grapheme cluster, and so that gets pretty gnarly pretty fast. And I think I'm going to pause recording now, and I will either maybe I will start a second video that explains what you have to do in order to sort of, or what I ended up having to do in order to maintain the state of the basically, in order to maintain the to be able to iterate over characters while allowing them to span leaves. And so perhaps I will stop this video here and upload it now, and then tomorrow I will make another video with information about basically explaining what this meant for the code of my rope, and I'll give you a little preview, which is it meant it was a big headache and it sucked, and I learned a lot, and I'm glad I did it. I never want to do it again. All right, I will see you tomorrow.